Mathis, who is going to tell us about code generation via metaprogramming in dependently typed proof assistance.
Oh, okay, it's working. Okay, so hello everyone. My name is Mathis, and today I'll be presenting work I did with Yannick Forster. So since this work, I started a PhD with Yannick and François Potier, also on metaprogramming, but this is work I did before. So I'll be speaking about code generation via metaprogramming in proof assistance. Okay, so all the main proof systems, like Rocq, Agda, and Lean, based on dependent type theory, provide powerful automation in several different forms. You can use tactics to build proofs interactively. You can implement macros for embedded DSLs. And the focus of this talk is going to be on boilerplate generation, which is the process of mechanically generating functions and lemmas. So a common archetype of boilerplate generation is something like this. You take as input an inductive type, say the option type, and you write a metaprogram which will generate, say, some induction principles, Boolean equality, printing functions. So many proof systems already allow you to do this. So the issue is that there isn't a consensus, unfortunately, on how to do metaprogramming. There are many different frameworks you can use. Rocq even has 4 different frameworks. Users often don't know the pros and cons of each framework. And how they compare. So the focus of this talk is to do a survey of metaprogramming in these different frameworks, which are listed here. And we do this through a case study, which is implementing a metaprogram which derives instances for a specific type class, which I'll show. So the case study is this one. We consider this Functor type class, which is very useful when doing functional programming. And we want to derive instances of this for concrete inductive types. For instance, on the option type, this is how it looks. We want to write a metaprogram which takes as input the option data type, or inductive, and produces this map function. And we can do the same for lists, for trees, etc. It's always kind of the same pattern, so it makes sense to automate it. So we did an implementation of this metaprogram in each of the frameworks we consider. And we kind of use the experience gained from these implementations to highlight the pros and cons of each framework. So in the resulting time of this talk, I'll go over each framework and provide some amount of high-level insights regarding the pros and cons. And then we'll conclude with some insights regarding what we want in an ideal metaprogramming framework. Okay, so I'll start with OCaml plugins. So Rocq is implemented as OCaml, and so the kind of most traditional way, but also the most low-level way of metaprogramming in Rocq is through OCaml plugins. So a pro of this is that with an OCaml plugin, you can interface directly with Rocq's implementation. So you can, for instance, define new tactics, define new commands, and you have access to many features, like unification, type class resolution. You can extend the parser, you can do virtually anything. Another advantage of OCaml is that OCaml has a very good ecosystem. It has a performant compiler. It has some tools like an LSP package manager, etc. But that's kind of where it stops. Then the cons of OCaml is that OCaml only proposes a very low-level API to build terms. You have to be very explicit when constructing terms and manipulating the AST. For instance, here are a couple functions which build terms. Make app is fairly easy to understand. You take a term and an array of arguments and you apply it. Your constructor is the AST. But now you want to build a case expression and you have this monster here where you have to, well, it's very difficult to understand. Using OCaml, you have to give lots of low-level details, such as implicit arguments, universe instances, the relevance of binders, obscure information relative to dependent pattern matching. And all this information is usually inferred automatically when you write Rocq programs. Another con of OCaml is that it uses De Bruijn indices in the AST representing terms. And if you've ever used indices, you know they are very easy to get wrong. For instance, here is a random Rocq term, and if you look at the body, you can see here we have raw integers, and in general it's very difficult to manipulate them. You need to shift them. It gets very error prone. Okay, so that was it for OCaml. Then I'll go over MetaRocq, which is another metaprogramming framework for Rocq. So in MetaRocq, metaprograms are simply Rocq programs. And the way you can kind of manipulate programs is that MetaRocq exposes an inductive representing the AST of Rocq terms. And you can just write functions on this. Then you can access kind of the actual implementations of algorithms such as unification and type checking, which are implemented in OCaml via a trick, which is going through a monad, the template monad, which I like to compare to the IO monad in Haskell. And so you have a couple of functions. For instance, tm make definition is a function in this template monad, which adds a definition to the global environment of Rocq. So in this way, you can kind of mimic the definition or lemma commands. A pro of MetaRocq is that you have basic term quotations, which are kind of a high-level API to build terms. So you have this tm quote function. You give it any term, and it gives you back the AST representing this term. So using this, you can kind of elude some level of low-level details. And then the last advantage of MetaRocq, which is for the moment mostly theoretical, is that you can reason on your metaprograms, because MetaRocq also formalizes most of the type theory of Rocq. You can use this. For instance, you have a typing reduction a reduction relation on terms. And you can kind of reason on metaprograms, but it falls short as soon as you're using operations in the template monad, because there is no specification for these operations. The cons of MetaRocq are that it uses De Bruijn indices, and in general it has almost the same term representation as OCaml. Term quotations, while they are somewhat useful, are also too basic. For instance, you can't quote terms with open variables, and you can't alternate between quote and unquote, which is something other frameworks have and is very useful. And lastly, programming in Rocq can be actually quite difficult for this kind of programming because you don't have any input-output. Functions need to terminate, which is a bit restrictive in writing metaprograms. Working with exceptions can be difficult, and in general, monadic programming can be a bit of a pain. Then I'd like to speak about Agda, and Agda's metaprogramming API, which is called the Reflection API, is actually very similar to MetaRocq, in the sense that metaprograms are simply Agda programs, and the equivalent of the template monad is the type checking monad, here TC. And Agda provides the same kinds of basic term quotations through the monad. But now a difference is that Agda handles the prover state. So what I mean by the prover state is the local context and unification state. All of this is handled internally in the type checking monad, which relieves the user from the need to kind of thread it explicitly. And in general, monadic programming in Agda is quite nice from my experience. Cons of Agda are, well, De Bruijn indices, same as the other ones. The term representation is actually quite constrained. So for instance, terms are beta normal by construction, so you can't have a lambda abstraction in the head position. And let bindings are erased or inlined during elaboration, which means metaprograms don't have access to these features. It is a bit annoying, especially for late bindings. It causes issues with local type class instances and so on. Okay. Then I'd like to speak about LTAG2, which is mainly a tactic programming language for the Rocq proof assistant, but can also be used to do a bit of metaprogramming. So here, I think an interesting kind of observation is that tactics provide actually quite a nice high-level API to build terms. So here is an implementation of the map function of option types using only basic tactics like instro, destruct, and constructor. And the code is fairly readable, and most importantly, it generalizes quite well to arbitrary inductives. And that's, another advantage of LTAC2 is that it manages the proof state, so like the global environment, unification state, etc., in an imperative way. So you don't have to carry them around, and instead you can imperatively query them and modify them. So you don't even need to work in a monad, which is quite nice. And then LTAC2 has basic term quotations. Cons of LTAC2 are that, well, actually tactics are actually quite hard to reason about when using them in kind of this programming style. And this is due to many reasons. For instance, tactics perform implicit backtracking, which is useful in proofs, but not so much here. And they also work on an implicit goal. So when you're using tactics in an interactive proof, at each tactic step you see the goal which updates. But here, when you're using them to build a metaprogram, you have to kind of imagine what the goal looks like and how the tactics will affect it. And it's not super easy sometimes because tactics use many heuristics. And then LTAC2 has quite a weak low-level term manipulation API. So while the tactic side is very nice, the term level API it uses the Brownian indices as other representations, and many standard functions are missing, and so on. And lastly, LTAC2 is mainly a tactic language, so it's missing some crucial metaprogramming features. For instance, you can't declare new constants using LTAC2, or you can't write commands. You can only write tactics. Okay, so LP is, I believe, the last metaprogramming framework for Rocq, we'll survey. And it's a language based on logic programming and lambda prolog. So it uses higher order abstract syntax to represent binders, which is quite different from the other frameworks. And so here, this is admittedly a bit difficult to read if you've never learned LP. But this would be the function constructor of the term type. Term would be ASTs. And you can see that, so this would be the name of the binder, the type of the binder, and the body of the binder. So here this HOAS representation for binders means that variables, well, functions are simply represented as LP functions. And this is quite nice to use in our experience. Then LP actually has very powerful term quotations because you can nest quotations and anti-quotations. For instance, this is a definition of a predicate in LP, which is kind of a function. And you can see here I can use the double curly braces to enter quotation mode. So now I'm using Rocq syntax. And then I can escape this using LP colon and parenthesis to go back to LP. And going back and forth like this provides a very powerful programming mechanism. And lastly, LP manages the proof state in a similar way to LTAC2, which is quite nice. Cons of LP, that logic programming is quite a big paradigm shift. And it can be a very steep learning curve, and some standard tricks are sometimes unintuitive. And then some aspects of the language are kind of unintuitive for those used to Rocq or to other proof assistants. For instance, it has implicit backtracking. The type checker can be very permissive, and sometimes it lacks representation for structured data. For instance, when writing this function with like a dozen arguments, I would have maybe liked records or stuff like this. So then I'd like to talk a bit about Lean. So the pros of Lean is that, actually Lean's elaborator is mostly bootstrapped, so written in Lean itself. And metaprograms are simply Lean programs. But difference with MetaRock and Agda is that since Lean is implemented in itself, you automatically have access to the complete Lean implementation. And then a specificity of Lean is that it uses the locally nameless binder representation, i.e. bound variables use the Brownian indices and free variables use names. So this is just an example of how to build this Lean term. So you would go like this. You would bind the variables one by one, and then at the end, with this function make lambda fvars, you would replace the names with indices. And so although under the hood there are some indices, you never see them, you always interact with names. And in our experience, it's also very nice to use. There's none of the downsides of the Brownian indices. Okay, and then Lean has powerful term quotations in the same style as LP. You can nest quotations in anti-quotations. And programming using monads is quite nice in Lean. So meta programs use this special meta-M monad, which is now, this is not really like the IO monad in Haskell. This is really a real monad implemented in Lean. It's just like a kind of state monad. And Lean has good support for monads at the language level with various notations. Now, cons of Lean, and this is quite a big one, is that the term representation is also quite constrained. And this became apparent when trying to build pattern matching or fixed points, especially complex fixed points. And this is because Lean has a term representation quite different to other proof assistants, in that fixed points are librated to recursors. And so this maybe makes for a simpler theory or implementation, but recursors for nested inductives, which are supported by our implementations, except this one, can get quite complex in general. So our Lean implementation is actually less feature complete than the other ones. Okay, so now that I've went over the pros and cons of each framework, I'd like to gather some amount of insights from this. First of all, we got this big table of recurring issues in metaprogramming frameworks. Obviously, oh yeah, I forgot to mention we have a preprint online, which you can go look up if you want to look this table. But here the main observation is that every single column has a bunch of red crosses. So we don't have yet a perfect metaprogramming framework or language. So now regarding ideal metaprogramming features we want in a framework. Well, first of all, we believe that the choice of the AST is very important, especially the binder representation. Unscoped deburn indices are clearly not the way to go. And then some frameworks use nicer representations, such as HOAS and locally nameless. Term quotations and especially anti-quotations, so the ability to nest quote and unquote is very important. Then effect handling is very important for metaprograms, because although they can seem pure from a first approximation, you need both generic effects, such as printing, non-termination exceptions, and also domain-specific effects, such as manipulating the prover state. And then lastly, we believe that verification of metaprograms could be desirable, not so much for users, because the output of metaprograms is always checked a posteriori. But we believe this could be useful for developers of metaprograms so that you can catch bugs earlier. So future work, well, an interesting direction is to extend this study to other proof assistants or languages, such as Idris, Hull, Beluga, or maybe try out other case studies. Then we also want to develop a metaprogramming framework based on our insights, most likely by extending MetaRock, and this is my PhD, which I started at the beginning of the year. And in particular, we want to think about verification of metaprograms and using like dedicated program logics to verify effectful metaprograms, maybe even separation logic for the eval map. We'll see what works well. Okay, thanks for your attention. And the code for the different implementations is on GitHub. We also have a preprint online, which just got accepted to ease up. Thanks.
What language was best for implementing this Functor implementation?
Oof, it's hard to say. I think all had significant flaws. I think overall the best were probably LP was quite enjoyable, and Lean also, despite the big flaw that, well, fixed points in Lean is really annoying with metaprograms. Yeah.
So you mentioned one of the issues with the directly hooking into the ML for Coq was that you had to use very complicated constructors, right? And you had to do a lot of boilerplate and deal with de Bruijn indices.
Yes.
So I was wondering, let's say we use either another system or a language which has macros, like for for argument's sake, Rust. You have a relatively complicated kind of procedural macro that lets you do kind of quotations and anti-quotes that then, desugars to the code, because I've been experimenting a bit with this, because, most of the locally nameless stuff, which is probably the representation you'd want to use for this, can be done at compile time, and you can have like a little DSL for this. How much do you think that would make it easier to use? Like, would that make the correct approach be to do the ML stuff and then have a DSL to like avoid the boilerplate? Because I feel like the problem with like, domain specific things is that when you want to use them outside the domain, you suffer. And that's just.
Yes, so there's several aspects to this. It's definitely something we've thought about, and I think it could be a valid approach. The issue with this specifically for a camel, so you'd rather use something like a PPX or something like this for a camel. The issue is that when you want to do kind of these quotations, they provide some very nice features based on the global environment. For instance, at quotation time, you can check if the global constant is declared or not, and stuff like this. And it's not so clear to me how to do it when you're writing a separate plugin, because then you don't know what the global environment is at compile time. You could maybe think of inserting OCaml code directly in Rocq files or whatever. Yeah, it would be Rocq files, same thing as LP does. And in this case, you would have access to a global environment. It might be a way to go. And in general, yes, I agree that it's a very good observation that you probably don't want to use a domain-specific language, because if you use the general-purpose language, such as OCaml, Lean, or even Rocq or Agda, you get lots of things for free. For instance, libraries and tools. That's definitely an important observation.
The functor instances that you wanted to generate doesn't really need to be inside the proof assistant. So have you compared it with other programming language that are not proof assistant but still provide some meta programming capabilities?
Mm-hmm. So yeah, the limitation here to proof assistance is mostly administrative, because we don't have time to survey everything. I think something that maybe makes more sense is to limit to, actually I don't know, it's kind of arbitrary where you want to draw the boundary. You could think of comparing with Idris, which is more of a programming language which has dependent types, but whole would also be interesting, like Isabelle and stuff like this, maybe Beluga. So at some point, well, this was kind of a work on a limited time, so we had to stop somewhere, but we're planning to, I'm in touch with people who probably want to do like an Isabelle implementation and stuff like this, which would be interesting.
Yeah, let's get the last one as the next speaker is setting up.
Adrian Lehman has a eGraphs plugin for Rocq that is interfaces directly with the Rocq LSP as an alternative to directly having a Rocq plugin. I don't know how generally applicable that is, but have you thought at all about using the LSP for metaprogramming?
So I think it's quite a different approach to metaprogramming, because with the LSP you have kind of access to a model of the whole document, whole Rocq document. Here you're more like writing custom, it's kind of a smaller scale metaprogramming where you're writing custom commands and tactics. Yeah, and I don't know what I can say more, because I'm not so familiar with interfacing with the LSP and what tasks you use this for.